You're listening to the Future Tech Health Podcast with Richard Jacobs. Until I reached age 40, I never realized the obvious, that we all have medical issues, or we at least have a family member or close relation that has, or will have them in the future. Medicine and biological systems are the final frontier. Until we've conquered death, figured out how life began, cured cancer, and understood our purpose in the universe, there's a heck of a lot to talk about when it comes to our health. Future Tech Health means I'll be covering futuristic topics that are actually already in clinical trials, or even starting to appear on shelves or by prescription, or available for your own use. We dive deep into stem cells, CRISPR-Cas9, the science of sleep, epigenetics, medical testing, cancer, ketogenic diets, stem cells, aging, regenerative medicine, and more. My goal for you, the listener, is to learn from these podcasts. You may very well learn something that may change the course of your life for the better, steer you towards a new career, or give you insight into addressing a serious medical problem. Remember, however, this podcast and its content is informational in nature only. No medical, tax, legal, financial, or psychological advice is being given. If you enjoy the podcast, please listen, subscribe, like, and share it with friends. Thank you. Hello, this is Richard Jacobs with the Future Tech and Future Tech Health podcasts. And I have John Ho. He joined the Department of Electrical and Computer Engineering at the National University of Singapore as an assistant professor in 2013. And he got his PhD under the supervision of Professor Ada Poon at Stanford. He was a National Defense Science and Engineering Graduate Fellow. And his PhD thesis focused on wireless power transfer to small-scale bioelectronic devices. We're going to be talking about his current research. And John, thanks for coming. How you doing?
I'm doing great. I'm calling in from Singapore. Yeah.
Oh, okay. Yeah. Well, thanks for calling in from so far away.
Thanks for taking Yeah.
Yeah. So tell me, what's your research about now? What are you working on?
Yeah, so generally I work in the field of bioelectronics. I'm interested in applying electronic devices to diagnose or treat diseases. And the reason that sort of makes sense, if you think about maybe the very first bioelectronic device, that would be a pacemaker. And I think most people know what a pacemaker is, a device that can go to your heart and basically solve cardiac arrhythmia. We can make the heart beat at the proper rate, right? And so it's kind of fascinating to think about that as, as just like a new type of medicine, really. Kind of the pacemaker is the first example of a device that electronic device that we can actually put into the body and actually solve a medical problem. And generally, that's what the field of bioelectronics is excited about. We're excited about using these devices to kind of give us new approaches to study and also to treat these diseases.
What are the diseases you're looking to focus on, or the type of devices you're looking to work with?
Yeah, so absolutely. So since the pacemaker, there's been an incredible number of bioelectronic devices that have come out. Examples would be a cochlear implant. That's a device that can restore hearing. There are pill cams, essentially little cameras that you can swallow that you can use to study the stomach and the gastrointestinal tract. So these are all kind of general examples of bioelectronic devices. So in my group, we're working more on the technologies behind these devices. We're interested in a lot on the wireless side. So my PhD was on wireless power transfer. We were studying how to, for all these devices, one of the major challenges is that they all run on batteries and those don't last forever. And so we're interested in looking at ways to send energy into the body. So this is kind of a way to increase the ability of our technologies to kind of access different parts of your body. So we generally, in my group, we work on kind of the technology behind these devices, and we also work on kind of building devices for different applications. Generally, the story behind that is we're interested in kind of improving the way that these devices can target our body. So you think about how like a pacemaker, why that pacemaker works. It's kind of interesting to think about in terms of precision in time and space. So if you think about, the way your heart beats, I can control it by putting a device into my body to kind of target that very precisely in space. So I can put a device in that only affects the heart. And also I can time it. I can actually, stimulate it every second. And that's not something you can traditionally do with, with kind of medical pills. just by swallowing drugs, I couldn't do that kind of things. And so we're interested a lot in this idea of spatiotemporal precision. How can we put devices in your body that allow us to target, these different processes in your body very precisely? And so to give you a more concrete example of that, we've been working a lot on one example of photodynamic therapy. So this is a way that we can use these essentially devices to target drugs. So we've been exploring this for use in cancer. So in cancer, one of the the traditional form of treatment would be chemotherapy, right? You take a drug that goes throughout your body, and that affects, and there's many side effects associated with that drug, kind of activating everywhere. And so we're interested in kind of using light as a way to target that drug. Can I turn on the drug only at the place where I want and not have it turn on elsewhere? That means I could potentially kind of get the therapeutic effects of chemotherapy without the side effects. And so light is a very powerful way of doing this. We can actually design drugs that are specially light activated. And we've essentially built these devices that can actually deliver light into our body. So the challenge with light, of course, is that light generally doesn't go very deep inside my body. I can't see through my body, for example. And so that's an example.
I don't know. I mean, what does that mean? Why would you direct light inside the body? What would you hope it would accomplish?
Yeah, so the idea behind that was to use the light to specially turn on a drug at a particular location inside the body. The contrast to that would be chemotherapy, right? Like a drug that goes everywhere in your body. So can we kind of have a drug that circulates through your body, but only turns on at a specific time and a specific place? And that way, for example, if I know where a tumor is, in the case of cancer, then I can actually turn on the device right at that place where the tumor is and have it activate there and not have it affect the rest of the body.
Right, you wouldn't want it to act systemically, I understand.
Mm-hmm.
So what's an example of this? What would you want to turn on, and how would you do it with light?
Yeah, so a cancer drug, for example. So cancer drugs, generally works by killing cells, right? And so it's essentially a poison, right? And so you want that poison to affect only the cancer cells and not the rest of your body. And so in general, in chemotherapy, we try to target cells that are rapidly dividing, for example, but that still affects healthy cells like hair. And so generally in chemotherapy, there are many horrible side effects associated with hair loss, nausea, and other processes. And so the idea behind targeting, kind of these targeted therapies is that I can have a way to turn on the drug just at the place where I want it and not elsewhere.
Yeah, I understand you wanted to turn it on at a certain spot so it doesn't act systemically. But
Mm-hmm.
mechanistically, how would you do that with light?
So it's very simple. You just have to shine light of a particular wavelength at the drug. So you design a certain drug that absorbs a certain color of light. And as long as you're able to get that wavelength of light, that color of light into that place, then you can kind of turn on this drug to start killing cells.
Has that been used? Have people been able to do that before with drugs?
Yeah, in fact, photodynamic therapy is already a clinical therapy, and they use it. It's actually a first-line treatment for skin cancer. So very often for skin cancer, you get a cream, for example, applied to where the cancer cells are, and you put your hand under a lamp, and that would kind of turn on those drugs, right only the place where you applied the cream, and kind of kill those cancer cells without affecting the rest of your body. The challenge with that, of course, is that we're only using it for skin cancer, even though it works very well. Why don't we use it for kind of the deeper cancers that I might care about, pancreatic cancer, brain cancer? The challenge, of course, is light delivery. How do we actually get light into, deep inside your brain, deep inside the pancreas? And that's kind of where bioelectronics come in. We've been developing essentially tiny light bulbs that you can turn on inside the body that can kind of turn on these drugs.
You'd have them on the surface of a device, and they would be activated remotely, and they would shine a light for a period of time, but you could be, once the device is implanted, then it could shine the light wherever it's needed.
Yeah, so that's exactly it. So once we have the device in place, we can actually shine light into that location and only selectively target that location. So probably an important question is that how do we, does it really make sense to put those devices in place? So really the key for us was to make this device really small. So these are not kind of big pacemaker type devices that you might imagine. They're actually tiny, about 2 millimeter size devices. We could potentially slip them in just with a needle, like a biopsy needle. And maybe even after surgery, after you've taken out the tumor, we could potentially leave these devices in place, just these little light bulbs. And if the tumor ever comes back, I can actually continue to treat that location without doing any additional surgery.
Well, I mean, when you implant devices, they don't typically just sit there. They tend to provoke an immune response, and they tend to grow things on their surfaces that might obscure an LED or something like that. I mean, so, if it's needed at a later time, I mean, I understand you want to make them small, and that's great, but that's also a smaller surface area, again, for films and all that to accumulate.
Mm-hmm. So I think that's an important question. Really, how does the body respond to these devices for a long time? Generally, what happens is a fibrosis will form around the device. Generally, the fibrosis is still somewhat transparent, so it won't completely block the light, and so that gives us at least a long window to treat to kind of get the light delivered. And of course,
a long window. What kind of time periods are you talking about?
Yeah, I think within our kind of the scope of our project, we've been focusing mostly on kind of animal studies, and these are all treatments done within 3 to 6 months of the kind of the tumor time. I think it'd be certainly studying the long-term response in humans would be a kind of a place for future work. But at least from the literature that people know about with these devices, I think within 8 years is certainly possible.
Well, why not, instead of just shining a light, why not also try to put a camera literally inside tissue and have it monitor tissue for a long period of time? Is that possible?
Right. So that's a fascinating idea. Of course, the challenge is inside the body is very dark, so a camera traditionally wouldn't work. So we still need a light to kind of see what we're doing. One of the challenges, of course, is the tissue is very three-dimensional, and so you need more than just a camera which can just image the surface. You want to you need some sort of like ultrasound, some sort of tomographic technique to kind of see kind of that three-dimensional volume. But certainly, I think interesting would be to put kind of biochemical sensors that could maybe detect markers of cancer if it were to ever come back.
Maybe if you put a camera in the digestive tract, it could see material coming and going if it stayed there in residence. I don't know if you need to have a series of them, but it might be possible to do something like that.
Yeah, so it'd be interesting to ask what the equivalent for cancer would be. I think biomarker may be the simplest way to do it, simply because cancers tend to release a lot of certain markers that go into the surrounding space and the bloodstream.
Yeah, okay. I would think there'd be plenty of places in the body that, again, we don't normally observe, but they could be observed in this way over a period of time. Mm-hmm. I mean, especially if you want to emit light onto a surface, you want to target it. Well, I guess if the drug will be in the surrounding tissue, you wouldn't need to target it 100% precisely. But if you're able to image the surface and see literally exactly where it needs to be applied, that may make it even more effective by doing that.
Yeah, so that would be a fascinating idea of maybe, of course, with a single device. I think you asked a bit earlier, what is the area we can cover? Of course, that depends on the amount of light we can get out of the device. The more light, the deeper through the tissue can go. But generally with these devices, we're getting coverage of about a centimeter or so. And so, of course, this is kind of at the boundary of useful right now because tumors can be quite large, many centimeters. So I think a more important development would be to be able to put multiple of these devices in. I can maybe scatter them through kind of where might suspect a tumor.
Or you put it in a place where there's a flow system in place so that the device sees a lot more material than just a static area where it only sees a centimeter that maybe doesn't change very much over time.
Mm-hmm, mm-hmm. Yeah, so one potential application of that would be, for example, circulating tumor cells, right? So it's exactly like flow. So with cancer, a challenge is metastasis, of course. The tumor will shed cells that goes into the bloodstream, and those end up somewhere else in the body and grow into a new tumor. And so I think a lot of recent work has been done on actually trying to take out these circulating tumor cells to stop the tumor from growing. So we could potentially place these devices near the bloodstream and had a way to detect where the cell coming by was cancer or a healthy cell, that would be fascinating.
Okay. Where are you at in making these kind of devices? Have you gotten to to make any prototypes yet, or how far along are you?
Yeah, so we've reached the so my group works a lot on the wireless technology, but really the key to making these devices small is to just take out the battery, really, because you look at any medical device, clinical medical device today, generally the largest part is the battery, right, and that's the part that runs out and just occupies the vast majority of space. So the key for us was to remove the battery, and so we instead of without battery, we still need a way to power this device. So we can put these tiny antennas onto these devices that can pick up power that we transmit from the outside. And so we've reached the state. So my group regularly builds these devices, and we can test them in animals. So we've demonstrated inside a mouse that we can suppress a tumor over time, and also in large animal studies, these are with pigs. We've been able to show that we can turn on these devices very deep inside, so about 6 centimeters down, for example, on the surface of the liver.
Okay, so after implantation, you can turn it on again at any level you want, pretty much wherever it's implanted in the body.
Yeah, so 6 centimeters would be quite a bit for a human. So we could potentially go maybe not quite anywhere yet. Of course, this depends on the size of the particular patient, but I think certainly enough to be useful for a lot of cases, like liver cancer, for example, or brain cancer.
Okay. So I guess you'd need an array of these devices in order for this to work.
Yeah, I think so far we've been testing single devices. We've been with a single device, we take out tumors that are about a centimeter in size, and so going for array, I think would be the next step.
Well, does the device permanently stay in there, or would it be removed at some point where it's not needed anymore?
So that's a good question. I think so far we've been envisioning just having the device stay in place, and that could be useful because one of the main concerns for any cancer patient is recurrence, right? I don't know if the tumor will ever come back. And so having that device in place, it could be, I like to call it a defibrillator for cancer. For a lot of patients that are at risk of having heart attacks, they'll have basically a stimulator implanted into their heart, and it may not ever be used. But if they ever go to cardiac arrest, this device will automatically reset the heart. And so this could be essentially something similar for cancer.
Since you need, you said you took the batteries out, so how do these objects function?
Yeah,
so power?
The way this works is with wireless power transfer, which is one of the expertise in my group. So essentially, we have a wireless transmitter that's kind of like a patch that sits on the outside, and that sends radio frequency energy into your body, and that's done using electromagnetic fields. And of course, a very important challenge with all that is to do so. To do that power transfer while maintaining very safe levels of exposure.
It sounds kind of tricky. I mean, the body is highly electrical. Why not try to have the device use, nutrients in situ, glucose and other nutrients that are being produced in the body anyway that all cells use?
Right. That's a wonderful question. I think that I think the general topic of using energy within your body is called energy harvesting, and it is an excellent idea, and there's many great engineers working on it. I say if you look at the state of the art at the moment, one of the challenges is just the amount of power you can collect is just not enough. It's maybe 100 times less than what you need to light up an LED at this point. And it's interesting and so one of the fundamental reasons for that is because what we care about is electrical power, right? So to light up LED, we need electrical power, and the cells in your body are very good at kind of performing chemical transformations using sugar, glucose, and the energy inside your body, but not very good at turning that into electricity. And so there's just there's not very many good ways currently to do that efficiently.
Okay. So what do you expect is ahead for the next year or so? What do you think is going to be possible? And then maybe the next 5 years or so, what do you think will be possible?
Yeah, I think so. With this particular project, I think certainly the next step is to really look at some clinical what kind of clinical needs for this kind of technology. When would it really make sense to put a device in your body to potentially suppress cancer. I think, fundamentally we are putting devices in your body. That's kind of a last resort kind of thing. If there's kind of very good treatments for a particular type of cancer already, then maybe this would not make so much sense. So kind of one direction we're looking in is to really look at cancers that are very resistant to current forms of treatment, and to see if this one might be able to make a difference. One very dramatic example of that would be glioblastoma. That is kind of the worst brain cancer, one of the worst cancers you can get. It's a type of brain cancer that's extremely aggressive, and so generally for these patients, I think the median survival time is just 12 to 15 months from diagnosis. And we're and this cancer is very resistant to existing chemotherapy, it always regrows after surgery. So you can take it out, but it will come back. And so we're wondering if, these kind of devices could be left in place after surgery to kind of try to suppress that tumor growth, because we know it's going to come back.
Well, how often would you need to use the device, do you expect, for various types of cancers? How often would you need to power it on? Or would you need to have it on continuously for a while?
Right. I think that's a really open question at the moment. With our kind of animal studies, we've been treating about once a week. So it's kind of a regimen. So you can come in, have the drug injected, wait for that to circulate, and then we turn on the device for about 15 minutes. So that's kind of the protocol we've been using. But I think it's an open question of whether or not continuous could be more effective, or this is enough.
Well, yeah, again, if it doesn't need to be powered on very often, that makes the power requirements a lot easier. They possibly could be stored up over time, over a week or two or a month, and you may be able to get plenty of power, even if you're only getting a tiny bit at a time. If you had some capacitance or storage, then maybe you would be able to use molecules and just slowly build up the charge, and then use it, and then build it up and use it.
Yeah, I think that's an excellent point. Whether or not we can. So I think that certainly works to the advantage of wireless power transfer. If you only need to turn on the device for short durations of time, I could just kind of sit down, hold the transmitter over me. That would be in contrast to something like a pacemaker, where you'd always have to be wearing the transmitter on the outside, which I think doesn't make very much sense. But certainly that also opens some opportunities for energy harvesting if you're able to store that over time. But I think the energy storage remains a bit of a challenge, right? Even with supercapacitors, they are leaky over time, and so you have to outpace that leakiness.
Yeah, it's just an idea to try it. I don't know if if it would work at all, or if you guys have looked into that. But I guess it's just a thought.
Mm-hmm, yeah.
Okay. Well, very good. What's the best way for people to find out more and maybe get in contact if you'd like to speak to anyone?
Yeah, I think so. My website is, of course, probably the easiest way. So I think you can see all the kind of the latest work from my group there, and my emails there. And I think that welcome for anyone to contact me on that.
And what's the website? What's the best one?
My website is a bit complicated. The URL is very complicated. But maybe I think if you just quickly Google, my name, John Ho, at NUS, that should be the first thing that comes up.
Okay, very good. Well, John, thanks for coming on the podcast. I really appreciate it.
It's been a pleasure to talk to you.
You're listening to the Future Tech Health Podcast with Richard Jacobs. Until I reached age 40, I never realized the obvious, that we all have medical issues, or we at least have a family member or close relation that has, or will have them in the future. Medicine and biological systems are the final frontier. Until we've conquered death, figured out how life began, cured cancer, and understood our purpose in the universe, there's a heck of a lot to talk about when it comes to our health. Future Tech Health means I'll be covering futuristic topics that are actually already in clinical trials, or even starting to appear on shelves or by prescription, or available for your own use. We dive deep into stem cells, CRISPR-Cas9, the science of sleep, epigenetics, medical testing, cancer, ketogenic diets, stem cells, aging, regenerative medicine, and more. My goal for you, the listener, is to learn from these podcasts. You may very well learn something that may change the course of your life for the better, steer you towards a new career, or give you insight into addressing a serious medical problem. Remember, however, this podcast and its content is informational in nature only. No medical, tax, legal, financial, or psychological advice is being given. If you enjoyed the podcast, please listen, subscribe, like, and share it with friends. Thank you.